thank you everybody. I want to start out with saying I throw a lot of links and references and I don't want you madly scribbling, so I'm putting everything on my GitHub and it's at the footer, so just relax, you'll be fine. Don't look at it now. Now is the garbage version as of a week ago. Wait until I get home where my GitHub password is, and then I'll upload the latest. Yeah. Also, important message, me disculpo porque solo sé un poco de español. Si desea hablar conmigo en español, maravilloso. Okay. Por favor, hable muy despacio y utilice grandes gestos. I would like to introduce my co-presenter, Chelnik, the PostgreSQL elephant. No relation to Travis Oliphant, I think. I don't know. I'm sure his presence will produce no bias in favor of Postgres in this presentation. So, we are not quite in the territory of the former Incan Empire, but we're really, really close. And you may sometimes hear that the Incas, quote, had no writing system. Not quite true, they had Incan string writing. This is a method for recording numerical data. It's actually really, really cool. Each of these strings represents a number. There's a cluster of a cluster of knots that represents a digit. The number of knots in the cluster and the type of knots in the cluster make a numeral from 1 to 9, or 0 if that place on the string is blank. And then the clusters, their spacing on the string indicates whether it's ones, tens, hundreds, thousands, or whatever. And then all of these strings are attached to the baseline string. And so they had actually a very sophisticated means of recording data. Now, other societies that did end up developing systems for writing down prose, for writing down long chunks of text, they developed those systems from earlier systems that were designed to record data. Data about taxation and ownership and things like this. Basically, the lesson is, if you want to create an advanced society, a prose writing system is optional. Recording data is mandatory. In fact, maybe even if you don't want an advanced civilization, this fossilized bone is 60,000 years old. It's a hyena bone from a Neanderthal camp. And these notches, nobody is sure, but it is believed that they are exactly what they look like, that some Neanderthal used these to record a number. That is how fundamental the recording of data is. So given its importance, where is it? If you go into, say, a basic programming tutorial, you're probably going to get only the barest information about how you actually want to store data and retrieve the stored data, which is a little bit weird. I mean, these machines that we work on, we call them computers. We should almost call them data machines, because almost everything they do is about data. I think that maybe one reason data storage gets short shrift is it's a big fat violation of the Zen of Python. There is not one way to do it. There are a ton of ways, and none of them are obvious, which kind of makes it less satisfying to teach, maybe less satisfying to learn. And so a lot of the time, you only get your knowledge about data storage a bit at a time as you need it. You may never have kind of backed off and had a chance to think about exactly what you're doing with data and why, and if it's the best way, and if there are better ways. I have been at this for a while. I started as a database administrator in 1999. I added Python to the mix in 2004. I'm on the verge of getting good at it, I like to think. And I have a bunch of thoughts. They revolve largely around the concepts of clarity and blur. That is to say, you want to be clear about what the various categories for handling data are, what are the technologies, what are the techniques, what makes them different from each other. But then the cool part is, once you understand those technologies, how can you blur the boundaries between the categories? How can you straddle the lines? How can you break down the barriers? So I have a potpourri of thoughts and techniques on both of these topics. If you ask a normal human being what that is, they'll say it's a table and it has rows. But if you want to sound like a fancy data person, say it's a relation and it has tuples. Now, is that just snobbery? You know, kind of. But if you think about it, This word, Venus, and this term, 224.7 days, I would say that they're not data, because they don't mean anything until you say there's a relationship between them. Venus orbits the sun in 224.7 days. Now it's a piece of data. Now it means something. And so a table tells us the relationship between the otherwise meaningless pieces of data within it. It fits it into this matrix and tells you, all right, now I know how big Mars is. Awesome. A table is one particular shape to express this relationship in. It is not the only shape. So one of the things you want to do is think about what shape you want to use to express the shape of your data. I'm terrified to ask this. Am I the only one here old enough to remember a telephone book? Oh yes, thank you, okay. A telephone book is a classic key value store. When you know someone's name, that is the key. You take it to the telephone book and you find their phone number. That is the value. It's a one-dimensional structure. It's super efficient. It's super easy. It's easy to understand. And so a lot of the time, a key value store is all you really need. The Python standard library comes with a key value library called DBM, which is actually based on lower level stuff. And that allows you to use keys and values that are both byte strings pretty much as if it was just a regular Python dictionary. And it handles saving it to disk, and you don't worry about anything else. Now, if your values are more complex, if they have more data contained in them, then you may want to move to a Python standard library module called shelve, which just lets you store, more complex values. Your keys still need to be strings. You can think of shelve as the simplest possible document database. This value, if it's a Python dictionary or a list or a dictionary with some lists embedded and so forth, we call that a document. It kind of has arbitrary shape. And in the case of shelve, that can store those documents and it can give them back to you when you know the key. But just like the phone book, it doesn't have a great way if you want to do a different kind of query. If you wanted to use a phone book to look up everybody who lives on such and such street, it would take you a while. You would have to go through the book manually. And that's what you'd have to do with if you were using shelve as a key value database. Now the great thing is, this is completely normal Python. You don't have to learn a darn thing that you didn't already know. But there's going to be speed issues. Plus it's a little bit bulky. You have to spend a minute reading it to figure out what's going on here. And that's why databases that are built specifically to handle documents support query languages. Query languages are DSLs that are all about letting you get information from deeper in the database. So MongoDB has a query language, a query by example form. Elastic, of course, has their own query language. There's a variety. JQ is kind of a language for drilling down and filtering and plucking out pieces from within a document that is not tied to any particular database or any language. There are Python libraries for it, but that's kind of a nice cross-platform DSL, you might say, for querying databases. Now, when we get into the rectangles, the kinds of, the shape that we're most familiar with, we have, if you ask business people in your organization for data, they will probably give you a spreadsheet. Nice rectangle. If we were to pass around a sign-up form of some sort around here, that might take the form of a rectangle, a piece of paper on a clipboard, and it might say, name, phone number, email address, rectangles. They come very naturally. Python's most famous library for handling these rectangles is pandas, which expresses each one as a data frame. Then it provides a ton of really useful methods on that data frame. It also overrides the square brackets to do cool things like filtering and plucking out individual fields. If you don't like if you like pandas, but it doesn't seem to apply to some specific need, maybe for scale reasons, maybe you want something that doesn't fit in memory, they're way at the bottom here. Again, the slides are online. There's a ton of pandas related libraries that you can use that either use exactly the pandas API or very pandas-like APIs, and all perform similar functions. Rectangles are great, but they don't always fit the data. This is so far so good. We're storing data about the moons of the planets. Ooh, but now there's Mars. Mars has 2 moons. So let's make a second column for the second moon. Okay, this is, I guess it's a data smell. It's not a code smell, but it's not something you want to do because it introduces a ton of problems. It's less problematic to denormalize this data, to basically use repetition to smooth over the problems with the data's shape. There are multiple moons, but that's okay. We're just going to record Mars multiple times in the data. And in fact, we're going to record multiple times the fact that Mars is about 0.11 the mass of the Earth. So that takes extra disk space, and it also provides the terrifying possibility that somebody may edit one of the masses of Mars, but not the other, and then the database is not consistent. So how bad is it? It kind of depends. Once we throw the moons of Jupiter in there, it's getting really bad. So that is why we often talk about normalizing data, which basically means splitting this up into multiple rectangles, and then there's a relationship defined between those rectangles. So that there's a rectangle to store the moons, and a rectangle to store the planets. Once you've done that, pandas can join those 2 different data frames and give you a result that, ironically, it's pretty much like our denormalized version. We get the repetition again. We're saying Mars twice and Jupiter who knows how many times. But at least this time the repetition is not stored on disk. Ultimately, underneath on disk, all these facts about Jupiter are only stored once. And then we just present it to you with some repetition when you do this join. I got this far without mentioning SQL. You're not going to go that long without SQL ever again. SQL is, of course, the most famous way to get at these tables, and it has its own very well-known syntax for doing joins. I've talked about this as a relational problem, but it can be a document problem too, because even though in a document store you can choose the arbitrary shape that you want, you can still run into the problem of, am I going to repeat or am I going to break this structure up? If my data includes, I want to know about the atmosphere of each planet, and what are the molecules in the atmosphere, and what are the characteristics of those molecules? Well, now I'm storing carbon dioxide twice, and I either need to break that apart or just deal with the repetition. So there's no great answer to that. Either way, you're paying a price. So many times you'll go to using SQL. And the most basic way to do that is just to put together a string of SQL and issue it from within Python. That's been possible for ages thanks to DP API 2 modules. But if you're considering doing that, please look at Records by Kenneth Reitz. The same person who did requests brings that love of nice APIs into using raw SQL. So if you haven't seen that, check it out. The most famous way to straddle the boundary between SQL and Python is with an object relational mapper. With an ORM, you can kind of forget about the fact that under the covers there are joins between these tables and just go into it like it's a good old-fashioned Python. Look, here's my Planeta object and it has Lunas, and I loop over them. Fantastic. I didn't have to think about relationships, but the only reason I didn't have to think about it is because first I just created a whole bunch of boilerplate to define these tables in the terms that the object relational mapper understands. There's about 2 screens full of this. And unfortunately, there's a variety of ORMs to choose from, and each of them has somewhat different syntax. So you get good at one, and then you move to another project that's using a different ORM, and you're not really starting from scratch, but you need to learn a lot more. You can get around some of the boilerplate problems if you act strategically and either define your tables in the ORM and then have that write the table definitions out to the database, or create them in the database and then use reflection to find out that structure from the point of view of the ORM. Because writing out this big definition, both in SQL DDL and in the ORM, would suck. Another thing, I've been showing SQL Alchemy, which is probably the most famous ORM. There are others, some of them are more concise, and the best rundown of these I can point you to is at the Hitchhiker's Guide to Python, which actually has great guides for a number of kinds of topics. If you're taking on a new kind of topic that you haven't taken on before, check out the Hitchhiker's Guide. It has some good pointers to useful libraries and so forth. And so check out the ORMs listed there. They might be more useful to you. Now, another boundary crosser, in between an ORM and writing raw SQL, there's a query building library like PyPyca, which is going to put together a SQL statement. So you need to understand all the concepts behind SQL. But if you really hate the syntax of SQL and you just want it to feel more like writing Python, PyPyca is great for that. The other cool thing is that it's composable. If you're writing a SQL string, you need to gather up all your filter conditions together and then put them together and use it. And if you throw in more filter conditions later on, sorry, it's too late, the boat already sailed. Whereas with PyPyca, you can keep on plunking in new conditions as you go. In fact, you can even mix up the order in ways that SQL itself would never tolerate, and it writes it back out for you. Another cool possibility, PugSQL is sometimes described as an ORM, but it's really, it's a library which lets you define your queries with regular plain old raw SQL. So you can do everything that SQL does without having to, Google, how do I do this in my ORM? But then each of those goes into a SQL file in a directory, and then you can import those in your main Python code. And you use those queries then much, much, much more like they were simple Python functions. And it feels cleaner. I like it a lot. Give it a try. Finally, last major paradigm I'm going to mention is the graph, because this can represent a whole variety of relationships in this great big web. And you will often visualize it as a graph. Underneath, it stores a bunch of pieces of information. You have a node Luna, another node Tierra, and an edge saying Luna orbita Tierra. And graphs are also great when this is recursive. The moon orbits the Earth, orbits the sun, orbits the center of the Milky Way galaxy, orbits other stuff. Graph queries are great for that. And graph query languages define ways to write those queries with DSLs. Unfortunately, not a single DSL. There are significantly different query languages that various graph databases have defined. So again, proliferation of APIs. And this you can write knowledge graphs that in theory can become incredibly intense. You would rarely visualize the entire thing, but that's what the query is for, to withdraw the subset of this that is of interest to you. Like if you want to know which planets have an atmosphere which is toxic to Taumiba, you could use a graph database to pull that up really easily. So I have talked so far as if when you define your database, when you decide on a database, all the other decisions are kind of implicit. Now I know how I'm going to store it. Now I know how I'm going to query it. And that is actually not necessarily true. If you're creative and you search around, you can find ways to break up these decisions. So just because someone says, well, we're going to use a SQL database, that doesn't actually make all of your decisions the way you may have expected it to. For example, Postgres offers the HStore, which is essentially a key value store hosted right there within Postgres. There's the PostgreSQL JSON type, which is really nice. This is not just throwing a string of JSON into your database. This allows you to query within that JSON structure. It allows you to define indexes that are specific to that kind of query. So it really lets it work like a document database, including performance-wise. Pretty amazing. Look into that if you're considering a document database. Another thing you can do is put one class of database on top of another. Some specific examples. FerretDB is essentially MongoDB. I mean, it uses the same API as a document database, and yet it's hosted on Postgres. Apache Age, a graph database, which takes the form of a Postgres extension. Actually, if you take advantage of advanced SQL, like the recursive CTE, you can do graph queries, these crazy recursive queries, within Postgres. Now that's going to be some heavy-duty SQL, but you can do it. Hang on a second. Is this entire talk just cheerleading for Postgres, telling you to do everything in Postgres? Chelnik? Okay. Listen, Chelnik. Cover your eyes, because we are going to talk about SQLite. So SQLite is up at the simple corner of this kind of matrix of possibilities. Most people are familiar with it, and they love it for how easy it is to use for quickie projects, for something that runs just on your machine, for a one-user app. There's, of course, it's supported right within the Python standard library. It's so easy. It really rocks. You can even use SQLite for application files where you weren't thinking of something you were going to use a database for. You just want a file format for your application. The SQLite docs include a great document on why you might want to use it that way. However, a lot of people assume that simple means weak. If it's great for simple, easy stuff, it's not also good for big, hardcore, serious stuff. Does that sound familiar to anyone? Has anyone ever been told, oh, Python, that's just a scripting language. That's not so good for this serious stuff. Well, it's really not any more true about SQLite than it is for Python. So in particular, SQLite can handle large volumes of data, and it can handle large numbers of processes connecting and using that data. So it's great when you're publishing, say, and then sending that data out to lots and lots of different people. SQLite works fine. Really, the only thing that doesn't work well is if you have a lot of connections trying to write at the same time. Then you're toast. So don't use it for that. But when it's more of like a model of publishing from a single source, really, really look at SQLite. Simon Wilson wrote a great article about the baked data pattern, which is where you just tuck a SQLite file in next to whatever server you were running. And that can be a ton cheaper if you're, say, hosting an application. They usually offer you a simple server cheap and storage cheap, and they try to gouge you on the database. So don't let them sell you a database, just use SQLite. I'm bringing up Simon Wilson partially because I want to talk about Dataset, which is this amazing project which allows you to browse and visualize a SQLite database crazy easy. All I had to do to get Dataset running on my machine was pip install it and then run Dataset and point it at my SQL file, and then I get this nice little data tool that lets me do things like I can navigate through, I can check out the moons that are associated, I can pop back up here, I can query, let me see, I can customize this query and run it. There is really a neat variety. There are a bunch of data browsing and visualization tools, but I don't know of any that are so easy to get up and get going as SQLite. In fact, as long as we're talking about crossing boundaries, how about that PyIodide, huh? Bringing Python into the browser, is that something else? Crossing the browser Python boundary? Well, Simon has gone ahead and implemented Dataset with PyIodide so that it can run in the browser. There is no server. The reason I put this big, ugly URL up here is because this part just goes to dataset.io, downloads Dataset into your browser window. That's the only place it goes. And then it goes to the other URL, downloads a SQLite database. In this case, it's just statically hosted on GitHub. And then you can browse that data with no server anywhere running anything. So earlier I showed you Dataset running on my machine, but with this URL, any of you can browse that data just like that, running in your browser. Which is great because every time I start thinking about hosting a server, I start to panic. It sounds complicated. I love hosting things statically. So I love breaking down that boundary. And then SQLite can actually do a lot of this cross-platform stuff too. There are ways to use it as a document database, or as a graph database, or as a full text. You can index fields for full text search. Another way to break boundaries is to stop worrying about where the data is hosted, but actually use data federation to leave it where it is. If it's in a different database, if it's in a flat file, whatever, just query it from a central place. And this is something that Postgres rocks at, so you can come back, Chelnik. because it supports foreign data wrappers, which are basically libraries that let you reach out from Postgres, treat external sources as if they were Postgres tables. You can query from them. You can even write to them, depending on the specific foreign data wrapper. Here's one for Mongo. There are ones to reach into a Parquet file. So if somebody tells you, we have to use big data, no sweat. And there are so many wrappers, I'm not even going to try to show you them all. They're really easy to write. The quality does vary. Sometimes you see one, it's like, this is going to be great. I was like, I wish you'd written some docs, but, and they're not always, some are read-only, some are read-write. Nonetheless, they're worth looking into. Some of them look into really crazy sources of data you wouldn't have thought of. I believe there's one to query the smart bulbs in your house as if they were Postgres tables. I haven't tried it. SQL itself goes outside places where you think of as where a relational database goes. It's really easy to send data into and send data back out of pandas. So if you're a pandas jockey, no problem. You can kind of dovetail that nicely with SQL. JupiSQL is a project that lets you run SQL within a Jupyter notebook, and it has a ton of conveniences there. If you're thinking, wait, I thought there was a library to do that called IPython SQL. Thank you, that was mine. JupiSQL is a recent fork of it. The Plumber has started to just like zoom ahead on development, and I really appreciate when a personal project turns into something that I can sit back and just say, hey, look at how cool this is. I hope that happens again and again. It also provides a handy way to generate a pandas data frame, starting with a SQL query. And then all these engines for big data that go against Parquet files and Abra files like that, I mean, they may belong to the post-relational database era, but they still support SQL. In fact, that's pretty universal. And then if you're doing extract, transform, load jobs and you haven't tried out dbt, what are you doing with your life? It allows you to host SQL queries as the core of your transformations, but then it does all the eyes verbs. In other words, you can organize and visualize and make your SQL queries from spaghetti into a really tidy, rational set of transformations. I was at an open space at PyCon a couple years ago, and we were talking about data transformation technologies, and the consensus was everyone hates everything that isn't dbt, but they love dbt. And then SQLite and Postgres both have kind of generated a family of related database technologies. Often these are like the cloud-based ones. So if you're interested in one of these good old-fashioned databases, but there's some limitation that you want to get beyond, look for these similar databases that springboard off them and use similar APIs so that you can keep on using that community experience and personal experience and yet maybe get more power that you need. Order and freedom. In an old-fashioned CSV, it is really clear what the fields are. There's no confusion there. In fact, in a relational database, when you want to add a new field, you actually have to run some DDL code. Whereas, say, if we're using a document data store, we can just all of a sudden decide, hey, I want to store whether or not a planet has a ring. That's nice and it's easy. One little problem, a little typo here, oops, but the document database didn't object. So that could start to create some confusion. And even beyond just literal typos, it just becomes harder to see, hey, what are all my fields? Tell me about my database. What does it look like? Both for your own eyeball and for tools that might want to introspect your database, it can be useful to have a defined schema, even if a document database doesn't require it. That's kind of the idea behind JSON schema, which is used to validate and establish a structure behind a document. The other cool thing about JSON schema is that it makes other technologies possible. And this reminds me of what Lukasz was saying this morning about typing, type hints, which were first used just to provide clarity, but pretty soon they started to empower other technologies like data classes. I love data classes, but if you work with ORMs, no doubt you have looked at your data class and looked at an ORM definition and thought, they're so close. Why are they different? Why can't they just be one thing? And the great news is that in SQL Alchemy 2.0, there's a little mix-in that you just add to your ORM definition, and then it works like a data class. And so these two have been brought together. That's a boundary that I was dying to see crossed. That's important for laziness, and I'm not talking about the laziness of loading data gradually. I'm talking about my laziness. I don't like writing code. So these technologies that establish the structure of your data can be used in a lot of useful ways. For example, there are libraries to generate fake data for testing. So that's a task I don't have to do. Once I've got either a JSON schema or I've written a pedantic definition or anything like that. If I don't even want to do that much, I just want to look at that data and have somebody else figure out what the data class is. There's a module that'll do that. It's better than I expected it to be. It's called Data Model Code Gen. Point it at data, and it'll give you a data class or a pedantic definition. That's pretty cool. I started to research what kind of automatic converters are available to go between different formats for describing data. I eventually gave up on making a complete map. This is only the beginning. It was going to be maybe my complete keynote, and I realized I just didn't know enough about it to do it. But I think we're approaching the point where somebody could write pandat or pandata, which would be like pandoc for document formats, only this would, given any manner for specifying data, it could generate any other just by gluing these tools together. So if anyone wants to write it, go for it. I did not have time. I am going to make an appeal now for one kind of, for clarity that should not ever be blurred. Please, 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 please. Units. Always units. There's no such thing as a distance. There's distance in kilometers, or in meters, or in light years, or whatever. There's no such thing as a cost. There's a cost in US dollars, or Colombian pesos, or euros, or whatever. Unfortunately, the best way I know of to provide that clarity is just to tack a suffix onto the field name of every field, which is kind of a pain. I love the Pint library in Python, if you've seen that one. That is fantastic for handling units once you've got it within Python. I don't know any comparable technology that is useful for actually going out into the database itself. If anyone else knows of one, I would love to hear about it. But you can attach metadata to a SQL column or a SQL table. This capability has been in SQL practically forever. I very rarely see it used, which breaks my heart, because code comments can be important, but I think you always need data comments. There's barely any piece of data in the world where you can just throw an attribute name on it and have that completely and utterly answer all the questions about the data. So please, 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 use comments in your SQL. Then you can view them, like in PSQL, just say \d+, and you can see those comments, and not forget the metadata. And that's really important, because getting back to our Kipu, I mentioned that we know how to read the numbers on Kipu. That's fantastic. Unfortunately, that's not all the information that's in a Kipu. Every string is tied to the base string with a different kind of knot. I mean, not different for everyone. There are a variety of knots which are used to tie those strings off. And the strings are generally made with a variety of colors of yarn. It is believed that that encodes information about what the string means. There's your metadata. Unfortunately, how to read those details has been lost. We don't know how to read the metadata on Kipu. There are thousands of these that have this really cool information about the Incas. And all we can see is numbers, not their actual meaning. But I don't want to end on a bummer note. There's a database called OpenKipu for storing all of the information about these Kipu. And it's published open source. That's fantastic. In fact, they publish it in the form of a SQLite database. And because it's a SQLite database published on the web, you know what was coming. There's the URL. And there it is. And so you can actually check out all this data. It's probably more intense than anybody who isn't an archaeologist is going to get into. But the really cool thing is I did not do anything at all to make that available other than put together the URL. And I'm just really, really charmed by going from the most up-to-date open source technology and reaching back through time and handshaking with this Incan technology to bring the data to the world, you know, maybe that's going to let scientists at some point reverse engineer the metadata and we'll at last know what those colors and what the particular form of the knots mean. So, I was nervous. I went a little fast. Thank you all very much. Chelnick thanks you all. And I hope that whatever your data issues are, you will remember that there are probably possibilities you haven't explored yet. If you didn't pick it up at a talk or with your previous reading, just go and Google. It's incredible how often you just assume that a solution exists and look for it and you find it. It's a crazy world. Thank you.